Hello, everyone, and welcome back. My name is Mr. Cobalt, and in this video, we're going to talk about writing Lewis dot structures and giving hybridization of various different molecules. So let's get into this. So in this problem, we're told that cyanamide, H2NCN, an important industrial chemical, is produced by the following steps. So the first step is we have calcium carbide reacting with nitrogen. That's going to give us our calcium cyanamide. And then we're going to get, that's our CaNCN plus some carbon. And then we have our calcium cyanamide here. That's going to be an acid. It becomes cyanamide. And then it says that calcium cyanamide, CaNCN, is used as a direct application fertilizer, weed killer, and cotton defoliant. So it is also used to make cyanamide, dicyanamide, and melamine plastics. So again, here we have some reactions. So here we have our cyanamide and acid reacting to form the dicyanamide. Then we have some dicyanamide in the presence of heat and ammonia, and that's going to form our melamine. So this is a partial structure of the melamine. And then we're asked to answer a few questions. So I'm going to do one by one. So we have like A through E or F. So I'm going to start with A and then we'll go on to the others. So the first question is draw Lewis structures for NCN2-. That's the anion of calcium cyanamide. Then also cyanamide and dicyanamide and melamine. So I'm going to write out the Lewis dot structures along with their resonance structures. So let's go ahead and start with NCN2-. So whenever you're writing Lewis dot structures, follow the steps. If you don't know what the steps are, I'll go through steps relatively quickly, but see my video on how to draw Lewis dot structures, and I go through all the steps. I go through a lot of examples, so that video is going to be very helpful. So here for NCN, I'm going to draw my skeletal structure. So I'm going to add up the electrons, the total number of electrons. So 5 for each of the nitrogens, that's 10. 4 for the carbon, that's going to be 14 total. And then don't forget the charge, and that's 2 electrons. So negative means you got to add electrons to your total. So that's going to be added 2. So I have 16 total valence electrons. And then when I do my structure, I'm going to do my skeletal structure. So it's going to be NCN. So that's 4 electrons. I've got 12 more. I'm going to put lone pairs on here. On the outer atoms first. That's all of the electrons. So carbon needs 2 more bonds. So I'm going to move lone pairs from this nitrogen to form a double bond, and I'm going to move a lone pair from this nitrogen to form a double bond. And there we have one Lewis structure. Don't forget the brackets. A complete Lewis structure for an ion requires brackets with the charge on the outside. So now I have one Lewis dot structure, but this can be a resonance structure because I can move electrons around. So what I can do is I can move an electron from this, or lone pair from this nitrogen, make a triple bond. That's going to push the electrons from one of these bonds onto the nitrogen because carbon can only have 4 bonds. So if I draw that out, so that's going to end up being N triple bond C single bond N, and then I'll have 3 lone pairs with the 2 minus. And of course, I can go the other way, right? So I can move this lone pair here, make a triple bond here, and then one of the electrons in one of the bonds here will be pushed on as a lone pair here, giving me a single bond on that side. So that's another resonance structure. So in this case, it'll be a single bond on this side. Like so. So here's the resonance structures for the first one, your anion of calcium cyanamine. So now what about this one? So we have cyanamine. So then we'll write that one out. So these 2 hydrogens are bonded to that nitrogen. So if we add up the total number of valence electrons, we get 2 for the hydrogens, 5 for each of the nitrogens, and 4 for the carbon. So again, it's going to be 5 plus 5 is 10, plus 4 is 14, plus 2 is 16. So we have 16 again. So now we'll draw the Lewis dot structure here. So these 2 hydrogens, where are they? These 2 hydrogens are on the nitrogen here. Like so. Then we have the carbon, and then we have the other nitrogen. So that's 1, 2, 3, 4, 5, 6, 7, 8. So now we're going to give lone pairs to the outer atoms. So I have 16 total. I used 8, so I have 8 more. So I'm going to put lone pair 1, 2, 3 lone pairs on that nitrogen, and then this nitrogen needs a lone pair. So I used up 8 electrons, so I've used up all my electrons, but notice that carbon needs 2 more bonds. So what I can do is I can move a lone pair from this nitrogen, make a double bond. So I'll put a double bond here. And then I can remove one of the lone pairs here and make a double bond. So now I've got one of the structures. Again, this can have resonance because the electrons here can push over here to form a triple bond between the carbon and nitrogen here. Because carbon can only have 4 bonds, one of these bonds are going to have to break, and the electrons are going to be pushed on the nitrogen, like so. So then what I'll have is I'll have the nitrogen with the 2 hydrogens again. This time I'll have a lone pair bonded to the carbon. I'll have a triple bond like so. I cannot have a triple bond here because again, I have 2 bonds here. And then if I have a triple bond, that's going to give me 5 total bonds. Nitrogen cannot have an expanded octet, so that is not allowed. So these are the only 2 resonance structures for this molecule. Next, we have dicyanamide. So dicyanamide is this formula here. So let us go ahead and write that down. So I'm going to write it down here. So I have 2 of these. So the way this is going to look is I'm going to have N bonded to C, bonded to N, bonded to C. And then I have these 2 NH2 groups. So here, I'm going to give myself some room over here. So I have N, C, and C. And then I have, an NH2 over here. So I'm going to have nitrogen with 2 hydrogens there. And then I'm going to have a nitrogen with 2 hydrogens there. Okay. So now that's my skeletal structure. How many valence electrons total? Well, it's 5 per nitrogen. So that's 5, 5, and 5. That's 15. That's 2. So I have 2 nitrogens here, 2 here. That's 4 nitrogens times 5. That's 20 total for the nitrogens. 4 for each carbon, so that's 8. So that's 28 total so far. And then I have 2 hydrogens on the inside times 2. So 2 times 2 is 4. So that's going to be 28 plus 4 is 32. So I have 32 total valence electrons. I used 2 per bond. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 18. If I subtract 18 from 32, that's going to give me, let's see, 14. So now that I have 14 electrons left, the next thing is to give the outer atoms, give the atoms a octet as much as possible. So I have nitrogen here, so that needs 3 lone pairs. That's 6. This nitrogen needs a lone pair. This nitrogen needs a lone pair. That's 10. And this nitrogen needs a lone pair as well. And so when I do that, I'm going to get a double bonds. And I still need to put in 1 more. So that should be 14. So 1, 2, 3, 4, 5, 6, 7 times 2 is 14. So I used up all of the lone pairs. Now I need to double check to make sure everyone has an octet. You'll notice that this carbon and this carbon does not have an octet. So we need to make double bonds. So a lone pair from this nitrogen can make a double bond here. This one needs 2 more bonds. So I'm going to move a lone pair from this nitrogen, create a double bond. I'm going to remove a lone pair from this nitrogen, create a double bond. So now that carbon has a full octet. And now this one needs a full octet. So I'm going to move a lone pair from the nitrogen on top, make a double bond there. So now everyone is happy with an octet. So here I have one possible Lewis dot structure, but there is resonance possible. So what can happen is I can move a lone pair, right, from the nitrogen here, make a triple bond here. That's going to push one of the pairs of electrons in the bonds onto the nitrogen, creating a lone pair there. So then if I draw this out, so I'll have N triple bond C with a single bond N, lone pair, double bond like so. And then I'll have the carbon with the 2 nitrogens again. Each nitrogen has a hydrogen, 2 hydrogens, and a lone pair. And so this is another possible resonance structure between these two. And finally, melamine. So here I have to finish the structure because you'll notice the structure is not complete because there's a lot of atoms here that don't have a full octet. So what you can do is we can put a double bond here, right? This carbon needs a double bond. This needs 4 more electrons. So I can put a lone pair here, a lone pair there, a lone pair on that nitrogen, a lone pair on this nitrogen, a lone pair on this nitrogen, and a lone pair on this nitrogen. Reason being is because for organic molecules, you do have the bonding patterns. Nitrogen in organic molecules loves to have 3 bonds in one lone pair. So here we have lone pairs. Here we have 3 bonds, and now we're adding a lone pair for the bonding pattern. Here we have 3 bonds with the lone pair, 3 bonds with the lone pair. Now this nitrogen needs 2 more electrons. This carbon also needs 2 electrons, so I can make a double bond there. Same thing here, I could put a double bond there, and then I could put a double bond here. So now you can see that each of the carbons and the nitrogens has an octet. So everything is good now. Now, the thing you want to notice here is that this seems like it's like a benzene ring. If you've seen a benzene ring, the only difference is if you got 6 carbon ring, like so, with double bonds, and those double bonds can switch, right? You can move electrons so that the double bond here moves to these 2 carbons. This double bond gets pushed to those 2. This double bond gets pushed to those 2. So the double bond switches over. Same thing happens here, right? So another possible structure would have the bonds in a different spot, right? So let me see if I can create another one smaller. So I'll give myself some room here. So here I have the nitrogen, and then I have carbon, carbon, nitrogen, nitrogen, carbon, and then you have the NH2, NH2, NH2. So instead of having the bonds here, you'd have a double bond there, a double bond there, and a double bond there. So just like benzene. So the bonds can switch places here. So here we have 2 different resonance structures for melamine. Okay, so we have our resonance structures for everything. So we're done with part A. Now we're going to move to part B. Okay, so part B. Part B says give the hybridizations of the C and N atoms in each species. So let's look at one at a time. So what we're going to be doing is we got to figure out what the hybridization of nitrogen and carbon in each of the resonance structures. It's going to be different for each resonance structure because, as you know, the hybridization is based on the complete total number of electron groups around the atom. So the number of electron groups is going to be the same as the required number of atomic orbitals you need to hybridize together to get your hybridized orbitals. So remember, I'll write it here. So we have our s orbitals. So we have our s orbitals, one s orbital, our p orbitals, and then we have our d orbitals if we need them. So we have our 5d orbitals. So the way that hybridization works, if you remember, is if I have a certain number of electron groups around my atom, then I need to take that number of atomic orbitals starting from the lowest energy s, moving my way up to higher energy orbitals, hybridizing them, and then getting the same number of molecular orbitals from the atomic orbitals that I hybridized. So so let's go ahead and look at this. So for this nitrogen here, you can see that I have 1, 2, and 3. The double, triple, and single bonds are all treated the same as far as group goes. So a single bond is considered one electron group. A double bond is considered one electron group, not two electron groups. And a triple bond is considered one electron group, not three. So here I have 1, 2, 3 electron groups around that nitrogen. So that means I need 3 atomic orbitals. So I'm going to take an S, a P, and a P. So I'm going to take these 3, hybridize them, and then I'm going to get 3 equal energy sp2 hybrid orbitals. So then this nitrogen here would be sp2 hybridized. Same for this nitrogen, since it's got the same bonding character. So it's got 1, 2, and 3. So this is also sp hybridized, or I'm sorry, sp2 hybridized. And this carbon has 2 double bonds. So each of these is 1 electron group. That's 2. So I'll take a 1s, and 1p hybridized. So that's called sp hybridized. So that's sp. So that's the hybridization of carbon and nitrogen there. What about here? So here you'll see that I have 1 lone pair, 1 triple bond. That's 2 electron groups. So I need an S and a P. So that's going to be sp hybridized. Carbon here has 1 single bond, 1 triple bond. So that's 2 groups. That's sp hybridized. Again, because I'm taking 2 groups, I need 2 groups. That means I need 2 atomic orbitals, and I need to hybridize those to get 2 molecular orbitals. So that would be S and P. Okay, and here I'm using molecular orbitals according to valence bond theory, not according to molecular orbital theory, just making that clear. And so with this nitrogen, I have 1, 2, 3, 4 electron groups. So I need 4 atomic orbitals, spp. So that's sp3 hybridized. So sp3. And for this one, basically it's switched. So here I have 1, 2, 3, 4 electron groups. So I need spp. So that's going to be sp3 hybridized. Again, the carbon here has 1, 2 electron groups, so I need S and P, so that's sp hybridized. And then here I have 1 electron group and 1 electron group, that's 2, so I need S and P, so that again is sp hybridized. Okay, so that's it for those resonance structures. Now, what about these? So you'll notice here I have 1 double bond, 2 single bonds. That's 3 electron groups. So again, I need 3 atomic orbitals. 1, 2, 3. Those are going to be hybridized. So it's sp2 hybridized. So this is sp2. This carbon has 2 double bonds. So that's 2 electron groups. That's S and P coming together. So sp hybridized. And here I have 2 electron groups with a lone, two lone pairs with a double bond. That's 3 electron groups. So I need 3 atomic orbitals. So that's 1, 2, 3. So that's going to be sp2 hybridized. I'll write it down here. sp2 hybridized. And what about over here? So again, I have 2 bonded hydrogens. I have a lone pair and I have a single bond. So that's 4 electron groups. So I need 1, 2, 3, 4. That's sp3 hybridized. So I'll write that up here. sp3. This carbon has 2 electron groups, single bond, triple bond. So that I need 2 atomic orbitals, s and p. So that's sp hybridized. And again, this nitrogen has 2 electron groups. I have a triple bond and a lone pair. So that's 2 electron groups. I need 2 atomic orbitals. So that's going to be sp hybridized. So far, so good. Let's go on to these two. So again, here this nitrogen, I have 1, 2, 3 electron groups. That's going to be sp2. Here I have 2 electron groups, 2 double bonds. That's 1 and 2, so that's sp. This nitrogen has 2 double bonds. That's 2 electron groups, so that's s and p as well, so sp hybridized. This carbon has 1, 2 single bonds, 1 double bond. That's 3 total electron groups. That's going to be spp, so sp2. So sp2 for that carbon. And these nitrogens are exactly the same. I have 3 single bonds, 1 lone pair. That's 4 total. 3 single bonds, 1 lone pair. Again, 4 total. So that's going to be spp. So sp3 hybridized. So this is sp3 hybridized. And this is sp3 hybridized. Over here, I have for this nitrogen a triple bond and a lone pair, so that's 2 electron groups, sp. Oops. So sp hybridized. Here again, this carbon has a single and triple, so that's 2 electron groups, that's sp. This nitrogen has 1 single bond, 1 double bond, a lone pair. That's 3 electron groups. That's spp. So sp2 hybridized. This carbon also has 2 single bonds and 1 double bond. So that's 3 electron groups. That's spp. So that's sp2 hybridized. And again, just like these two, it's exactly the same. So these are going to be sp3 hybridized. sp3 hybridized. Again, because you have 3 single bonds, 1 lone pair, that's 4 total groups. spp, sp3 hybridized. Okay, finally, here we have our melamine. So this nitrogen, so these 3 nitrogens are exactly the same. 1 lone pair, 1 single bond, and then the 2 hydrogens are bonded as well by single bonds. So 3 bonds, 1 lone pair, that's sp3 hybridized because it's got 4 total groups. So you need an S, a P, and a P to hybridize to get your sp3 hybridized orbitals. So this is going to be sp3, this is going to be sp3, and this is going to be sp3. Same over here, sp3, sp3, and sp3 for that nitrogen. Okay, so for this here, for the carbons, right, you could see all of these are the same. So you have 1, 2 single bonds, a double bond. 1, 2 single bonds, double bond. Here you have 1, 2 single bonds, double bonds. So that's 3 bonding groups, 3 groups, 3 electron groups. So that's going to be spp. So that's sp2 hybridized. So I'm going to write that here, sp2, sp2, and sp2. Same thing over here, 2 single bonds, triple bond. So all of these are going to be sp2. Oops, let me give myself some room. So sp2 hybridized for that carbon, sp2 hybridized for that carbon, and then of course for that carbon, sp2 hybridized. And what about the nitrogens? Notice that the nitrogens are all the same too. Lone pair, single bond, double bond. Lone pair, single bond, double bond. Lone pair, single bond, double bond. That's, again, 3 electron groups, so spp, sp2 hybridized. So all of the nitrogens are sp2 hybridized. sp2 hybridized, sp2 hybridized. Same thing over here. So nitrogen sp2 hybridized, sp2 hybridized, sp2 hybridized. And so that, ladies and gentlemen, is the labeling of your carbon and nitrogen atoms for every species giving the hybridization. Okay, let's move on to part C. Okay, so let's go on to letter C. So C says how many sigma bonds, pi bonds, and lone pairs are in a species. Fasten your seatbelt. We got to go through all of them again. So, but it's actually really easy because for sigma bonds, every bond, single, double, triple, has one sigma bond in it. So all you need to do is count all of the bonds for the sigma bonds. For the pi bonds, anything beyond the first single bond is going to be a pi bond. So if you have a double bond, one of those bonds is a single bond. The other extra bonds is going to be pi bonds. So for a double bond, you have 1 sigma, 1 pi. For a triple bond, you have 1 sigma and 2 pi, right? So it's actually really easy. So you just need to then count. It all depends on whether or not you have the right Lewis dot structures, the right resonance structures. If you got the right resonance structures, then it's just a matter of counting. So here, this species, I have how many? I have a double bond, so that's 1 bond, 1 bond. That's 2 sigma bonds there, right? So that's going to be 2 sigma bonds. I'm not going to write it down. So we have 2 sigma bonds here for that species. And we have 2 double bonds, so that means we have 2 pi bonds. We have a pi bond here and a pi bond there. And then for the lone pairs, you just count the lone pairs. So we have 1, 2, 3, 4 lone pairs for that one. For this one, again, here we have one sigma bond here, because remember, for every bond, there's one. Every bond between atoms has at least 1 sigma bond and no more than 1 sigma bond. So you can only have 1 sigma bond, because remember, the sigma bond represents the overlap of the bonding orbitals between the atoms along the axis of, that's directly between the atoms. You can only have 1 overlap there. Right, so 1 sigma bond here, 1 sigma bond here, so that's 2 sigma bonds. Here I have a triple bond, so in addition to the 1 single sigma bond, I have 2 other bonds. Those are going to be 2 pi bonds. So I have 2 pi bonds here. And then for the lone pairs, again, I have 1, 2, 3, 4 lone pairs. And then finally over here, this one is the same as this one, except now I have the triple bond over here. So again, the number of sigma bonds is 2. The number of pi bonds is 2 because of the triple bond. And the number of lone pairs is 1, 2, 3, 4 lone pairs. Okay. Next, here for this one, the number of sigma bonds is just the number of bonds total, not counting double and triple bonds, right? So again, if you have a double bond, there's only 1 sigma bond there. So we have 1, 2, 3, 4 sigma bonds, right? Now for the pi bonds, we have 1 pi bond per double bond. So we have a pi bond here and a pi bond there. So that's 2 pi bonds. And then for the lone pairs, we have 1 and 2. For this species, again, sigma bonds, we're just going to count one bond, one sigma per bond between the atoms. So here I have 1, 2, 3, and I have one sigma bond there for 4. So I have 4 sigma bonds here. The triple bond gives me 2 extra or 2 pi bonds. So one of these is a sigma bond, the other 2 have to be pi bonds. So I have 2 pi bonds here. And for the number of lone pairs, again, I have 1 and 2. So 2 lone pairs there. Okay, next we have this species here. So again, sigma bonds. Count the number of bonds that you have between atoms. Ignore the double bonds and triple bonds for now. So here I have 1 sigma bond here. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 sigma bonds. Pi bonds are going to give indicated by double and triple bonds. So here I have a double bond. So one of those bonds is a pi bond. Here I have a double bond. One of those is a pi bond. And I have a double bond here. So one of those is a pi bond. So I have 1, 2, 3 pi bonds. And the number of lone pairs is 1, 2, 3, and 4. Next, our other resonance structure. Again, count the bonds between the atoms, ignoring double and triple. So here I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So that's 9 sigma bonds. Here I have a triple bond. So that's going to be 1, 2. So I have 2 pi bonds here, and I have 1 pi bond there. So that's going to be 3 pi bonds again. And then for the lone pairs, it's going to be 1, 2, 3, and 4. One thing that you should notice is that the number of pi bonds, sigma bonds, and lone pairs is not changing between the resonance structures, right? So each of the resonance structures has the same number of sigma bonds, same number of pi bonds, and same number of lone pairs. Okay. And here we can see between these guys here. So again, for the number of sigma bonds, don't forget that these 2 hydrogens are bonded to the nitrogen. So that's easy to forget. So there's 2 bonds there. So we have 2, 4, and 6 bonds. Okay, so we have 6. We have 7, 8, 9. Okay, and so now we look at the bonds in the ring here. So we got 9 so far. So now it's going to be, if we start here, so that's going to be 10, 11, 12, 13, 14, 15. So we have 15 sigma bonds. Now, for the number of pi bonds, that's going to be determined by the double bond. So we have 1 pi bond here, 1 pi bond there, 1 pi bond there. That's 3 pi bonds. And for the lone pairs, we have 1, 2, 3, 4, 5, and 6. So 6 lone pairs because we have 6 nitrogens. Each nitrogen has a lone pair. And so that's it. And the exact same thing applies to this one. So this is exactly the same. The only difference is that the double bonds have switched places. And so that, ladies and gentlemen, is part C. Let's go on to part D. And so the question for part D is the ring in melamine planar? So where's melamine? This is our melamine right here. So is this a planar ring? Well, let's take a look. Look at all the atoms in the ring. They all have what hybridization? sp2 hybridized. So if you notice The reason it's sp2 hybridized is because you have 3 electron groups according to Vesper theory, right? If you have a certain number of electron groups, they all want to spread out equally around the atom. They want to get as far apart as possible because the electrons are negative. Negatives are going to repel, like charges repel. So this here, this carbon, because it has 3 electron groups, according to Vesper theory, is going to be trigonal planar, so that all 4 atoms are in the same plane. So this carbon is in the same plane as this nitrogen and this nitrogen. But then if we look at this nitrogen here, this is also sp2 hybridized and it has 3 electron groups. So that is also trigonal planar. So this carbon and this nitrogen and the lone pair and this carbon here are also all in the same plane. So this nitrogen and this carbon and this nitrogen are in the same plane. This carbon, this nitrogen, and this carbon are all in the same plane. And then you can continue, right? So this is sp2 hybridized. So this nitrogen, this carbon, and this nitrogen are all in the same plane. So, and if you continue, it's the same for all 6. So yes, all 6 of the atoms in this ring structure are in the same plane. And then you can see that here as well. So yes, they are all in the same plane because all of the atoms are sp2 hybridized, meaning they have all 3. They all have 3 electron groups, which means that they're going to be trigonal planar. All of them are trigonal planar, meaning they're in the same plane. Okay, let's go ahead and do part E. Okay, let's get into letter E. So for letter E, they're telling us, okay, so for dicyanamide, we're told that there are 3 different CN bond lengths, so they're not all the same bond length. We're told that it's not a linear molecule, and they want to know which resonance structure is the most important. So these are kind of linked together because the most important Lewis dot structure is going to kind of determine the overall shape and bond length and all that stuff. So that'll kind of explain these things. So let's go ahead and determine which of the 2. So we have this one and this one. Which one of these is the most important? So we're going to have to figure out the formal charges of the atoms. Now, the formal charges, if it's following your typical bonding pattern, the formal charge of the atom is going to be 0, right? So for nitrogen, it's going to be 3 bonds, 1 lone pair, so the formal charge is 0. So for these, it's going to be 0. So I'm not going to write it down for these. Hydrogen, again, is going to be 0. Carbon here has 4 bonds, so that's typical bonding pattern of carbon is if you have 4 bonds, you have 4, you're going to have a 0 formal charge. And then so for these, we have to look at the nitrogens. So when you're determining formal charge, it's the number of valence electrons for the atom. And then you're going to subtract out 1 electron for each bond that's bonded to that atom. And then you're going to subtract out each of the electrons for lone pairs. So all of the lone pairs you're going to subtract and 1 electron for each bond that is on that atom. So here we have nitrogen. So the nitrogen is in group 5, so it has 5 valence electrons. So if we do the math, we'll take 5 valence electrons, and then we're going to subtract each 1 electron for each of the bonds. We have 2 bonds here, so we're going to subtract out 2. And then the nitrogen has 2 lone pairs, so that's 4 electrons. So we're going to subtract out 4 electrons there. So 5 minus 2 minus 4, that's going to be minus 6. So that's going to be equal to a minus 1. So the formal charge on this is going to be a minus 1 for that nitrogen. And then for this nitrogen, again, same idea. So we start with 5 valence electrons. So here I'll do it again. So I have 5 valence electrons. I'm going to subtract out 1 for each bond. So I have 1, 2, 3, 4 bonds. So subtract out 4. And then I'm going to subtract out the lone pairs, but I don't have any lone pairs on the nitrogen. So that's a 0. So 5 minus 4 is going to be equal to a positive 1. So that's equal to +1. So then this nitrogen has a +1 formal charge. And the rest of these are going to be 0 formal charges for the reasons that I said just a moment ago. Now let's do the same thing over here. So again, these are exactly the same. So 0 formal charges for the atoms over here. This nitrogen has 1, 2, 3 bonds. So if we do the formal charge here, it's going to be 5 for the valence electrons minus 1 for each bond. So that's 3. And then we're going to subtract out 2 for the lone pair. We got 2 electrons there. We're going to subtract those. That's -2. So -3 minus 2 is -5. 5 minus 5 is 0. So no formal charge. And you can see the reason for that is because it's got the bonding pattern that nitrogen likes to have. The most common bonding pattern is 3 bonds, 1 lone pair. So nitrogen, whenever it has 3 bonds and 1 lone pair, that's going to have a 0 formal charge. So this is 0. Okay. And then here, we have for this nitrogen, again, we're going to have nitrogen N5, so 5 valence electrons, and we're going to subtract out 1 electron for each bond, so that's 1, 2, 3. So we're going to subtract out 3. And the 2 lone pairs, and again, it's 0 because, again, look at the bonding pattern. 3 bonds, 1 lone pair, so it's 0. So all of the atoms here have 0 formal charge. Now, when you're trying to decide which of the resonance structures is the most or more important, there's 3 things you want to look at. The first thing is the complete number of formal charges. How many formal charges do you have in your molecule, in your resonance structure? So the more total number of formal charges you have, the less important it is. So that you want less number of formal charges. So for example, here I have 1, 2 formal charges, and here I have none. So they're all 0. So this is not as good. So this is more important on that point. The second thing you want to look at is how large those formal charges are, right? So here we have 1, so -1, +1. Here we have 0 again. So again, this is more important based on that point. And the third thing you want to look at is if you do have a negative formal charge, that negative formal charge prefers to be on the more electronegative atom. And again, over here, we don't have to worry about that because we don't have any formal charges. So by all accounts, this is the most important or more important resonance structure compared to this one. Now, let's go back to the observations that were given. One is that the 3 CN bonds, the bond distances are different, meaning we should have different bonds. And you can see here we have a single bond, CN. We have a double bond, CN. And we have a triple bond, CN. That would explain why we have different bond distances. Single bonds are longer than double bonds are longer than triple bonds. And here they're all the same, right? So this does not fit the observation that we have 3 different bond distances for our CN bonds. And also you'll notice that we have here linear, but here we have here trigonal planar. We have sp3 hybridized or sp2 hybridized, and here we have sp. So this is going to be bent, right? So because this has a bent shape, because it's got a molecular geometry of bent, because we have 1 lone pair and 3 bonding pairs, or 2 bonding pairs. And here this is linear because we have 2 bonding pairs. So again, because this is the most important or more important species, the resonance structure here, this overall determines the characteristics of the molecule. And so that's why we see 3 different bond angles, 1, 2, 3 different bond distances. And it's not linear, which fits the fact that this is a trigonal planar electron geometry and it's bent on this around this nitrogen. That's it for this video. I hope you enjoyed this video. I hope this helped you out tremendously. If it helped you out in any way, then please, by all means, like the video, share the video, hit that like button somewhere over here. Also, subscribe to my channel. Help me out here, please. Also, when you do that, click on the notification bell up there somewhere. When you do that, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. I've already heard from a few of you. Some of you want me to do organic chemistry. I am planning on doing that, so stay tuned. I don't know when I'm gonna be able to get to that, but it's on the list. Finally, if you have a question, if you have a problem, if you have something you want me to go over, put that down below. I would love to do that for you. Thanks for joining me and have a great day.